starting off with a sort of big picture story, I thought I'd start with a picture of a power station. Does anyone recognize it? They all look like the same. They all look the same as each other, really, don't they? Some people here have lived in Oxford, so you would have been supported by this power station. This is Didcot power station. This picture is when it was a coal-fired power station, and it was burning at the time something like 3.7 million tons of coal every year. Just that one power station was burning 3.7 million tons of coal. And if you try and that's a big number, right? It's difficult to picture what that is. So try and do it in your head. Coal's a density of about 1, so it's about 100 meters running track, right? 100 meters by 370 meters. That's about the amount of stuff that was being funneled into that power station every year and then going up in the atmosphere. Okay, and it's amazing when you think about the solid material and then it's all in the atmosphere. And I think it's quite arrogant, really, that humans have spent so long thinking that we could get away with doing that sort of stuff and turning coal and oil and gas into CO2 and putting it in the atmosphere and nothing would happen. It's particularly arrogant because we had known scientifically for at least 100 years, since Arrhenius in the late 1900s, that if you put carbon dioxide in the atmosphere, it does lead to warming, and there's a clear expectation physically and indeed chemically that will lead to an increase of planetary warming. So I wanted to start with Didcot as a close to home example, but of course there are power stations. There's still more than 8,000 coal-fired power stations around the world. This process is happening wherever you go and causing that warming that Arrhenius predicted and that we're now experiencing. And this is the experiment we've been running on the Earth. You can see that it has indeed followed the physical predictions that we'd expect, and it's got warmer and warmer, with all of the warmest years on record basically being in the last decade. I'm sure this is information that you all know already. I didn't have time to update this, but this is a lovely website if you want to get up-to-date information about CO2 in the atmosphere, or methane or other greenhouse gases. So what I've been through so far, I think you all know, and actually I think everyone knows really, apart from perhaps the extreme arm of the Republican Party in the USA, pretty much everyone else agrees that CO2 in the atmosphere is causing warming and that this is a problem that we really need to fix, that climate change is a problem we need to fix. And that really became internationally recognized at Paris in 2015. It's been ratified since at one time or another by every country in the world. And that represented the moment of global agreement where we said, it's a problem and we really are going to join together to do something about it. That has been, I think, recognized, that consciousness around the world that we had to do something about it by the follow-up on one of the central goals of Paris. And that was the recognition that we had to get to net zero greenhouse gas emissions in the second half of this century to stabilize at 2 degrees. And if we wanted to keep the temperature anywhere near 1.5 degrees, we had to get to that net zero value in mid-century, so about 2050. And since that recommendation and agreement in Paris, lots of countries have signed up and made firm commitments to do that. In dark green, such as the UK here, there are legally binding requirements to reach net zero, often by 2050. Light green have got policy to do so, and brown are considering it here. So if you live from or you've got relatives or friends in one of the grey countries, start thinking about how you can do something about them. But in general, most of the world recognises that we really need to act to get to net zero, and we need to do that quite soon. So as I'm a climate scientist, or as someone who's been trained as an earth scientist, this is a bit of a moment actually where I think we can change the narrative. We've spent a lot of the time so far thinking, how can we tell people that climate is bad and climate is changing and convince people? That job is done. Okay, we finished that job. People understand that climate is bad and we've got to do something about it. And they also understand that it is changing and we need to be ready to adapt to it. And there's widespread recognition of that as well. So we now need to be thinking a little bit more, not about identifying the problem, but thinking about what the solution might be to that problem. And it's a theme I'll return to a few times. What are we actually going to do to meet the climate challenge, the climate crisis? So where have we been so far? I mean, I work in government at the moment, but I would say this even outside of government, that the UK has been a real leader in trying to address the challenge of climate change. And since the 2008 Climate Act, which committed us to reduce from our 1990 emissions down to only 20% of that level by 2050, we have made substantial decreases in CO2 in this country. And I might remind people, in case you don't know, that the Climate Act that initiated that was a Labour piece of legislation, and the Net Zero Act that I'll talk about in a minute is a piece of Conservative legislation. So these two things represent bipartisan agreement across the UK. And this shows, taken from one of the Committee for Climate Change reports, the emissions of greenhouse gases in 1990, and which was the reference year, and then where we'd got to by 2017. A rather simple graph that breaks things down into the really big lumps on here. There's some big success stories on here. Look at something like waste in blue. I'd say one of Defra's sectors, that's gone down really quite a lot. And red, of course, power has gone down a great deal as well. So we've changed the way that power is generated in the UK really quite significantly. Oh, good. This is how we've done it. I didn't realize it was going to be quite so noisy on your speaker system. But this is how we've done. That's Didcot. Yeah, that's what we started the lecture with. That's Didcot coal-fired power station. It doesn't exist anymore. Sorry, it's so noisy. What exists in place of power stations like that? Oh, should we just watch it again? Because it's so cool. What I love is when this tower collapses, it looks like a piece of cloth just like folding up on itself. Look at this. Yeah. There goes 3.7 million tons of coal every year, which is a good thing. And this is what's replaced it. I happened the same week to fly over to the continent. Probably should have been on a train, of course, but I flew over to the continent, and these are wind turbines underneath the plane. And this is what was replacing the energy and enabling us to remove the energy of the carbon from energy production. Now, again, coming back to the solution space for a minute on this slide, if you're a person who has worked in resources, trying to get resources out of the planet, like oil or gas, you need to stop doing that, and you need to start looking for rare earth elements. Each one of these wind turbines has got 350 kilograms of neodymium in it, and significant amounts of dysprosium as well, which is a really unusual, hard to find rare earth element. So that's the resource hunt now, is to find the metals that we need for the green transition and our less carbon emitting systems. So coming back to this slide again, so talked about some of the successes, waste and power, but there's obviously some things on here which haven't changed very much. Agriculture and land use, it actually looks like it's changed on here, but that's kind of a bit of a fudge in the numbers, and really that hasn't changed very much, and I'll show you that in a minute. Transport on here and buildings as well are really suffering from not changing very much so far. And furthermore, we know that the challenge is now getting harder. Okay, we've done the easy stuff. Knocking down Didcot's kind of satisfying, but now we're getting to some of the stuff that comes close to home and really is going to start to bite and be more difficult. But at the same time, we in the UK have legislated not just to meet that 20% target by 2050, going down to 20% in 1990, but we've legislated to go to zero by 2050. So the trajectory that gets us there has steepened. You can see the black line for our emissions was roughly on track to get to something like 20%, but it's not on track to get to zero by 2050. And we're going to have to steepen the curve and reduce our emissions even faster if we're going to get there. So this is a graph of emissions versus year, in case you hadn't worked it out. You can see on this graph as well the CBs, the carbon budgets, and these are also set in law by the 2008 Climate Acts that I mentioned. You can see we've done a couple of them, and we've now got targets that are set out here. At COP last year, or just before COP last year, the UK set its target for carbon budget 6, centered on 2035, and that was a reduction of 78% relative to 1990. And 78% is nearly 80%, right? So it's basically like bringing the end point of our ambition forwards by 15 years, so that we have to meet the ambition of the Climate Change Act by 2035. And it's making this a really big challenge. How can we strip out the rest of our emissions really quickly to meet CB6 and then keep going down to get to 2050 targets? So the UK has been thinking quite hard about this. And again, I'll champion the UK as a bit of a global leader in this area. We are the first country to really write down and publish a strategy for how the country might get to net zero. It's been criticised as imperfect. Of course it's imperfect, because we don't know how to do it yet. But at least it's a first attempt to write down in detail some of the ways that we think we might be able to achieve that. And the NetZero Strategy, which was published again just before COP last year in October, was accompanied by another publication, the NetZero Research and Innovation Framework, which laid out the research and innovation that was needed if we were going to solve the problem and fill in some of the gaps that we have in working out how to get to net zero. This demonstrates the UK really thinking hard about the problem of how we might achieve that net zero goal. I keep looking over at my slides as if the next one's going to be there. It's a bit of a lottery for me. I don't know what's going to happen. And when I press the button, oh yeah, here we are. So this is some of the thinking that has gone in, and now I'm going to bring it into first of all to government and then into Defra. So what we're trying to do, let's step back. We're trying to work out how to get to CB6 in particular and onwards. These are the documents that lay out how we're going to try and do it. And then this is a summary of some of the ways that we're organizing this in government, so you have a sense of the policy. So BEIS, the Department for Business, Energy and Industrial Strategy, it's just changed its Secretary of State, are responsible for climate mitigation. I should mention in passing that Defra is responsible for adaptation, but BEIS, as the department that is responsible for mitigation, is also therefore responsible for the UK meeting our carbon budget and our net zero goals. It's their job in government. So often the way government works is to apportion jobs to the different departments and let them lead on it. And BEIS then apportion in turn effort shares to other government departments. They divide it up broadly along the lines that the Committee for Climate Change have recommended and say to different departments, you've got to do this much and you've got to do this much. So my department in Defra, we're responsible for 4 sectors of the industrial system that emit carbon or greenhouse gases: agriculture, land use change and forestry, LULUCF, waste, and fluorinated gases, CFCs and such like. So we've got to do something about those, and the target that we've been set, I've already mentioned this target for the national level, 78%, and when you divide that out according to our share, we've got to make something like 51 million tons of CO2 or its equivalents per year, which is a big change. We're currently emitting something like 50 million tons of CO2 equivalent per year. So this is a really substantial change that we've got to work out how to do in the UK by 2035. And if I'm being blunt, we don't know how to do it. We don't actually know how to do that yet. And this is taken from a Defra internal document, which is very much a thought piece. So don't take this as a policy piece at all. This is just us thinking about what the scale of the challenge is. We know we've got some things we're already doing that cut emissions. We've got some things that are pretty easy and we can roll out easily. We've got some things that are more costly, but we know will work to reduce emissions. And then we get into this chunk of stuff that we don't really quite know how to do it. And a lot of the thinking, a lot of the research and innovation is in this red patch here, at least from a science point of view. How can we close that gap and work out how to strip emissions from agriculture and land use? The purple on here is other bits of the UK. So this is Defra's responsible for England, and this is what we're expecting the Scottish and other nations to do. So that's the scale of the challenge. It's sort of laid out here for you in one of the areas of Defra's activity. This is agricultural emissions. So again, lots of my graphs have emissions on one axis and then data on the other. This is agriculture now broken down into things like cows' methane production, or the nitrous oxide that comes from slurry that cows make in manure. And you can see that although there were some reductions in the 1990s, we've really not seen very much change in agricultural emissions for the last couple of decades. And working out how to change this is really quite difficult. You might say, particularly if you're a vegetarian, well, just eat less meat and dairy. You might better get rid of some of these down here. But remember that much of our farm system, much of our rural communities and our rural economic systems are built on farming systems that rely on meat and dairy production. So just making a big change to this is actually quite challenging, although from a CO2 emission point of view, we'd really like to do more to it. So that lays out the challenge in just one of the sectors, and it's one of my sectors in the Defra area. But other departments are thinking about their challenges equally as hard. So I'm just going to dive in. I'm going to move fairly soon onto a slightly different theme, but before I do so, I'm going to dive into one little bit of the UK NetZero Strategy, the document that I showed you the front cover of earlier from October last year. And this is a piece taken from the Natural Resources chapter, which effectively was written by Defra as our contribution to that document. And the bit that I've drawn your attention to on here, you might have time to read some of the others, and I encourage you to look at the whole document. It's really interesting. the bit I'll draw your attention to in particular is that the UK has committed 75 million of R&D money to really dig into these problems, work out what can we do to strip out some of the greenhouse gas emissions from agriculture, from land use, from waste, and from F-gases. And that's part of what we're driving forward in the science infrastructure in Defra at the moment. Okay, so Sarah's going to switch gears, and this is perhaps a bit of a switch to a figure that some of you might have seen before, but for those who haven't, don't worry, I'll talk you through it. So I've been talking about the UK up to now, and it's mostly about the UK and saying how we've got to do something about our own emissions. I'm going to come back to the UK as an example in a minute, but I just want to think globally for a second as well. And this is a figure that I think really changed people's thinking. It came out, it's from Fuss et al. In 2014, and it came out shortly before Paris in 2015. And what it's plotting on here is the emissions from fossil fuels against age, against year. So you can see, similar to the graphs I've shown you before, the sort of emissions that are now going up globally. So at a global level, unlike the UK, our emissions are tracking upwards with time. And then it's showing you predictions of what might happen in the future. I've said it's difficult to change systems. It's difficult to change agriculture. It's difficult to change every bit of our societal systems. And if you build models that try and predict how quickly you can do things like knock down power stations or change from meat production or change your transport system, these are called integrated assessment models, and they enable you to predict the maximum rate at which you can change carbon emissions into the future. And here are a few, well, quite a few of those integrated assessment models out to the future with different assumptions about how we try and change the system. And so in red here are ones where we basically carry on like we are until we start running out of resources, and the planet with that much emission going into the future gets to very warm temperatures way in excess of the Paris goals. So in order to do something that looks like Paris, we have to follow one of the blue trajectories on here. And those are changing the system as fast as we damn well think we can. So that's knocking down all the power stations, taking meat out of the system, doing everything we can as fast as we think we can. And if you look at that blue trajectory, what's really interesting and was really known from about this time onwards, 2014 onwards, that from a net carbon point of view, the average of those models at some point this century passes zero. That means we're changing from a system in which we have to, we're admitting that we're emitting, admitting that we're emitting, to a system where we have to consciously take carbon dioxide out of the atmosphere. So we have to do some greenhouse gas removal if we're going to be able to follow one of these trajectories. So this has become part of the thinking. Decarbonising, as I've showed you in the UK, is tricky. We think we can do a lot of it, but we probably can't do enough. We can get down, we probably can't do enough to quite get there without also sucking some of the carbon that we emit back out of the atmosphere again. And this changes the equation and sets up quite a few different challenges for us. I'll show you the same figure sort of schematically quickly. So on this one, this is net carbon emissions. This is net. So this is net zero effectively here, and it's going net negative over on this side. If you think about it, breaking it down a little bit more, so this is basically the same figure but in cartoon form now. If you carry on business as usual, it goes up and you get to a very hot temperature. If we manage to reduce steeply as fast as we can, emitting other greenhouse gases and CO2, it doesn't get us to a low enough carbon emission. So we also have to start doing some negative emissions, taking it out of the atmosphere really quite soon, this century, this decade, and then throughout the century. And that will get you on the trajectory that we need to meet carbon emissions. I think we need to ask Nina to go on mute, probably. So this figure is taken from a greenhouse gas removal report written in 2018 jointly by the Royal Society and the Royal Academy of Engineering. It's sort of, I chaired the group that wrote this, which is why I'm going to call on quite a few of the figures that came from it. You've seen a schematic that came from this this document already. This document fed into quite a lot of the UK thinking about what we might do on greenhouse gas removal. And probably the figure that I've put into my slides most often when I've spoken about it since is this one that plots out for you that makes clear that for a greenhouse gas removal technique to work, for you to suck carbon out of the atmosphere, put it somewhere, you have to do both of those things. You have to remove it from the atmosphere, and then you have to store it somewhere. And the ways in which we can remove it are basically through biology, through inorganic reactions, speeding up chemistry normally, or through an engineered process. And the places you can put it are on land, on land as dead stuff, under the floor, in the oceans, or in built environments, typically as wood, but sometimes as other products. You can see that on this sort of matrix, most of the boxes have got something in them. There's some idea that we might explore to suck carbon dioxide out of the atmosphere. But some of them are obvious, like trees up here, growing trees clearly does it, stores it. And I should mention that trees are plotted in green here because they're doing both of those things. They are extracting it from the atmosphere and storing it all in one go. Other things here, like BECCS that we'll come on and talk about in a minute, separate those two things. So you have to suck it out of the atmosphere with one process and then store it with another. I'll come back to this figure in a little bit. But just to say that this approach, this desire to do greenhouse gas removal, isn't just sort of theoretical and academic as it was in Fuss et al. In 2014, nor is it a policy ambition globally only, like it was in Paris. It was in the Paris Agreement. It's also built into UK projections. So here's a similar sort of figure showing emissions from different sectors for the UK now. And you can see that as you get out to 2030 and towards carbon budget 6, we have numbers that are below zero here. We've turned on greenhouse gas removal in the UK as well. But here's a bunch of interesting research to do. We've got to work out how we can do that. We've got to work out how not only can we decarbonize the sectors I've spoken about before, but also how can we start sucking carbon dioxide out of the atmosphere in the UK using the technologies and the nature, the land that we've got here. This is taken from, again, from the NetZero Strategy document that I showed you earlier. So again, I showed you how we're spending some money inside government on trying to decarbonize in Defra's sectors. Here are a couple of other big research programs that have happened or are ongoing as UKRI funded and BEIS funded efforts to understand specifically how we might help by greenhouse gas removal. So you can see on the left here, there's a £30 million UKRI greenhouse gas demonstrators strategic priorities fund. It's quite a mouthful, isn't it? Which is now running with 5 big demonstrators trying to see how you can use trees or biomass or biochar or enhanced weathering or, I knew I'd forget one more, to suck carbon out of the atmosphere. Peat, that's the last one. And on the right-hand side, there's another program which is being run by BEIS, more technology and industry focused to work out how we might use more engineered solutions to suck greenhouse gas out of the atmosphere. So we don't know how these work yet. We haven't found out. We're doing the research, we're doing the demonstration, trying to find out which mechanisms are the best mechanisms to achieve the greenhouse gas removal that we need in the UK to balance our budgets, and also that we're going to need globally, and indeed technology that we might sell around the world. In the Royal Society report that I showed you the cover of a minute ago, there was also a figure that tried to work out how specifically for the UK you might attempt to balance off different greenhouse gas removal approaches. And we don't know the answers to this, but this was a first effort to try and see how we might do it. And compared to the total amount that we think we need to strip out, this pie chart shows you what we thought in 2018 might be a good balance of the different approaches to greenhouse gas removal. And you'll see there's lots on here. I won't go through all of them, you'll be pleased to hear, but I will focus a little bit in the rest of this talk on 2 of the biggest ones on here. Briefly, I'll talk about BECCS here, I'll explain what that is in a minute, and then I'll talk more about enhanced weathering, which is an area that I've been researching in Oxford directly. But there's other techniques on here that you'll see, and I'm happy to talk about if you've got questions. So let's come back to this figure again that I showed you before, just to put these onto that framework. So BECCS, I'll first of all spell out the acronym for you, stands for bioenergy with carbon capture and storage. So it's a combination of growing stuff to burn it and then capturing the carbon that comes out and putting it somewhere. So that's why we've got one process to extract and one process to store. We'll talk more about BECCS in a minute, but you can see it relies on growing stuff, and then it normally relies on geological storage, putting it underground. The other one I'm going to focus on is enhanced terrestrial weathering. I'll say more about what that is, but this is speeding up a chemical reaction in soils in particular. So it's an inorganic reaction, and it's typically in soils. So let's quickly do BECCS. So I thought I'd mention BECCS kind of because it's the biggest slice of what the UK will probably do, and also because it was the thing that Paris talked about. When Paris was struggling to close budgets, the agreement there was basically, oh, well, let's just do it with some BECCS. Let's get some BECCS in, and that will help solve the problem. And that's clearly a rather naive assumption. You can't do quite that much with BECCS, and there's people in Imperial who've worked a lot on aspects of this problem, I know. But it's still worth thinking about it because it is one of the really major ways we might attempt to do greenhouse gas removal. And it's shown schematically here. I've run through it already. You take carbon dioxide by growing stuff. You stick that in a power station, not unlike Didcot, but now not burning coal. And then you normally expect to put the CO2 under the ground into a geological reservoir. Again, lots of areas for Imperial style research. I mean, I know that there's lots of geophysics going on about subsurface storage and such like in these sorts of challenges. Forms. So we in the UK, some of the research that we're doing is to work out what sort of biomass we might grow here if we're going to do more of this. We already do quite a lot of it, actually. If you, I should have put a slide in here, but there's a really nice app which tells you where we get our electricity from at any one time. And that app, if you look at it, biomass is nearly always in the top 4. So a lot of the UK energy already comes from burning of biomass. There's an aspiration that we grow more here so that we can burn our own domestic material as well and up the amount that we burn. And then also hopefully turn on greenhouse CCS as well. So we turn on the storage as well as the displacement of coal from the system. And here are just some pictures of the sorts of crops that I might work in the UK. Switchgrass here and miscanthus in the back there and bales of it up here. And we already grow about 20,000 hectares of miscanthus in the UK. So it's already a crop that's used here and we're planning to do more. So that's just a brief introduction to one of the technologies that's been most touted. Whoops, I've gone too far. Also, let me talk for my remaining time now about the other technology. And I'm going to spend longer on this because I work on it myself with some graduate students in Oxford in my remaining Oxford portion of my time. So enhanced terrestrial weathering does what it says in the tin, basically. It takes silicate minerals, like this is an example of a silicate mineral, reacts them, which they react naturally with CO2, but it's trying to speed up that reaction that you show here to generate what is effectively alkalinity, so free positive charge. And that positive charge ends up getting balanced by carbon, which has a negative charge when it's dissolved, and balances off the positive charge. So this reaction is consuming CO2 from the atmosphere and turning it into a dissolved bicarbonate ion, which you then hope will go down rivers and into the sea. So you can see it being practiced here at scale. This is out in, I think, Ohio, doing a test of this, somewhere in the States, doing a test of this sort of approach. Now, let's just think about the scale of this, first of all. I think it's always important when you think about the carbon system to bring it back to scale, because people often think, oh, well, if I fix my peat bog over here, or I fix my swamp over here, I'm really making a contribution. But it's only doing it if you're doing enough carbon to matter. So we've got to think about, would enhanced weathering do enough to really make a difference? And if you look at the scale of emissions that we've got, this is a slightly out-of-date figure, but we're up to about 40 billion tons of carbon dioxide a year that we're emitting globally to the atmosphere. If you look at that sort of scale, 40 billion tons, compared to weathering in the carbon cycle, you'll find that carbon is actually, so weathering is a very small flux. Apologies, actually this is in gigatons of carbon, not CO2. So you need to times the numbers on here by 3.6 to get into CO2. But you see the flux of weathering, these are all the different forms of weathering coming down rivers, is about, well, it's about 4 billion tons of CO2. So it's about a tenth of our emissions. So all of the natural weathering all around the world, it's happening everywhere on land, is only currently doing about a tenth of what we are emitting every year from burning fossil fuels. So you might say, well, that sounds a bit of a stretch then. How are you going to really make a chunk by accelerating that weathering? How are you taking a bite out of the emissions that we're making at the moment? Well, there is hope here, and there's hope because the weathering rate around the planet changes because of nature a great deal. And this is a model result, but it's well tuned to observations. And it shows you how much variation you get in weathering in different settings around the ocean. And it's controlled by temperature, by how much rain there is, and by how much fresh surface of silicate you bring into the reaction area. So the more fresh surface you bring and the more rain you get, the more that you can react CO2 with that surface. You can see there's quite a large range here. And if we take these sorts of models and we say, okay, now what happens then if you dump a whole bunch of material into soils, freshly ground up silicate with lots of surface area, what happens? And some of those models suggest that you could do really quite substantive amounts of carbon dioxide removal. And this is a figure, a couple of figures actually taken from a paper from the Sheffield group, who are probably the leading group in the UK who work on enhanced weathering. It's a paper by Kansas et al. This year, showing a couple of scenarios for what they think might be possible. It's a model result, and they're showing what they think might be possible for the UK. So I'll just put you back into a UK mindset. I've been off in global things, so coming back to the UK. And remember, our agricultural emissions at the moment are about 50 million tonnes of CO2 per year. And we're looking at numbers on this chart over here that go up to similar sorts of values as the whole of our agricultural emissions. And it's showing a couple of scenarios as you increasingly add more silicate to soils of how much we might expect to withdraw from the atmosphere because of enhanced weathering. This is a lower scenario where they've added less silicate to the material. So the modelling results at least suggest that it's not without hope that enhanced weathering could lead to sufficient uptake to matter. But let's just stop and think about this for a minute. I'm an environmental scientist, I'm a geochemist. And if you start thinking, this probably isn't an exhaustive list, but if you start thinking about thinking through the things that we might need to worry about before we did this at scale, here are some of the things that we should think about. And I'm going to run down this list rather than reading them all now. I'll run through them systematically. But I would say before I start doing that many people in earth and environmental sciences, if they look at a list like this, can start to see where their research might attach to some of these questions, or where you might find a way in. It's a bit of a call to arms really here, that whether enhanced weathering is your subject or some other aspect of greenhouse gas removal or CO2 reduction, I think it's really time for the research community to start thinking, where are the problems, where are the issues in that climate challenge where I can be most useful with my research and bring research to bear on those sorts of issues. Let's go through some of these. I'm aware that time is ticking on, so I'll try not to go through them too slowly, but I'll just run through some of them as an example of the types of research that we need before we can really start doing greenhouse gas removal at scale. So the first question is, where does the silicate come from? And how are we going to get the energy to grind it all up to expose all that surface area? We've got to find the material. That's going to cost us carbon to do so. And there's actually quite a nice demonstration of how big a challenge that is. If you look at how much electricity goes into grinding up minerals today because of the mineral industry. Something like 4% of all the electricity that's produced globally goes into machines like this in mines to grind up rock so that we can take out the iron or the cobalt or whatever it is that we want from that rock. So that shows you the problem. Okay, it's a lot of energy in grinding up material, but it also hints at a possible solution in that we've done a load of this already. And we've got great big piles of stuff sitting around from which we've extracted the mineral we want, and it's ground up fine already and ready to be spread onto land. So perhaps there are some shortcuts to do this grinding and we can get some material more easily. Now, this is a complicated figure, so I'm not going to talk through it in detail, but if you're interested in this stuff, it's from Liam et al., reference at the bottom there. And this is just an attempt to work out how much of that leftover mine tailing material is there that we might use for this purpose, working out for each mineral type how effective it is at greenhouse gas removal and how much of it's produced every year. And the bottom line for this figure is that you get around about 1 billion tons of CO2's worth a year of mine tailings that you might use to get you a good start onto greenhouse gas removal by enhanced weathering. Global estimate again. Sorry, I'm jumping backwards and forwards from domestic to global. So there are some routes into how we might find the material and how we might solve the grinding and energy challenge. Let's think next about the impact of spreading it on the soil. The last thing you want to do is stop yourself from being able to grow food, because that's obviously quite important. We need food to live. So we don't want silicate to damage the soil. We need the food to remain healthy. We don't want it to be full of toxic metals, so we can still eat it. We need to confirm that the alkalinity really is released. We need to basically measure it and evaluate the process, and that carbon dioxide is drawn down. And we need to know what happens to that carbon dioxide. Where do they go? Do they go down the rivers? Do they go to the ocean? And that's the next couple of slides that I'll talk you through quite quickly, but I'm happy to take questions on this. We're getting into the nitty-gritty of some geochemistry now. This is a study that was done by Frankie Buckingham. She's just finished her PhD at Oxford. Here you see her getting the core samples that she used for most of her PhD work in a field near Oxford. And her study was basically trying to work out the answers to those questions. Is the soil still all right? How much does it dissolve? How much carbon dioxide does it remove? Where does it go? You can see her experiment. She took those cores and put them on the roof of our building in Oxford, the Earth Science building, put rhizomes into the side so we could suck out the water, let the rain fall on it and the sun shine on it, and worked out what happens to those soils. If you then stir into the top of them crushed basalt, olivine, ash, steel slag, kiln dust, and agricultural lime. And these are probably the 6 leading candidates for things that we think might work and we might use for greenhouse gas removal. I won't talk through the rest of that. I'll just jump to some results quickly. This shows, oh, we've lost the axis on here. Sorry, this is showing you the amount of alkalinity released. And if you're not a geochemist, you can roughly equate that to how much CO2 is being taken up. So the more alkalinity you release, the more CO2 is taken up. And it's showing you the control, the average of 3 control cores here, relative to how much alkalinity was released or CO2 was consumed for the different treatments on here. Measured 2 different ways, I should say, to check that we get the right answer, 2 different geochemical ways. So you can see that Frankie's work is able to show us that olivine doesn't look very good. It's actually almost causing more carbon release than anything else. But there's some quite promising approaches, including things like steel slag here or cement kiln dust. Frankie was also able to think about the environmental limitations of this approach, including the fact that the rocks dissolve so slowly that you actually end up with a lot of the silicate left in the soil. And that means if you keep on adding more every year, as farmers are wont to do, and some of the models suggest they should do, the soil rapidly becomes silicate, and then you probably can't grow things in it very easily anymore. So there needs to be some assessment about how quickly you really can add another layer before we go to do this at scale. And some of the minerals that we tested also release a lot of quite toxic metals into the soil. So clearly you wouldn't want to eat carrots full of vanadium and arsenic. So that rules out steel slag, unfortunately, given that it's quite a rapidly reacting matrix. So this is kind of the punchline of Frankie's work. Just some of this has just been published and some of it's in review. And this is showing the UK potential if you were to do this pretty much on all agricultural land that's available, and you put the different types of treatment down, shows you how much uptake of CO2 we might expect compared to the lowest bound from that model that I showed you, the model that suggested we might be able to compensate for all of agricultural emissions by enhanced weathering in the UK. But that was 50 million tonnes a year. And what we're finding is we're getting very much smaller amounts in a real experiment, in a real core from a real field. So empirical evidence at this stage suggesting UK maybe not quite so promising. It does look like there's, this is not the end of the story though, because it does look like there's a lot of control by things like the water flux. Oxford is quite a dry place, and there might be some other places and other options that would be better. I'll skip over that. So I'll quickly run through rivers now. I don't think I'll do the oceans. I'll skip them out, but happy again to talk about them if people are interested. But the next bit of the chain as you go through enhanced weathering is, okay, so you've dissolved some of it, it's in the soil, you've got the calcium that's released, you've got the bicarbonate that's been absorbed. Where does it go? And it's going to go through the soil into the river and then down into the ocean. The next bit is the river. What's it going to do in your river? Suddenly all this extra material in the river. And does it make it all the way down the river, or does some of it come out on the way and therefore not be so helpful to climate change? This is work done by another PhD student who's still in Oxford, Kirsty Harrington, shown here. And she's done a few things, but I'll show you the work she's done, particularly to model the impact of what you do in UK rivers if you pursue this at scale. And in particular, she's been thinking about two things: how much stuff might go down the rivers if you assume that the silica saturation stops the dissolution. So silica, when you dissolve silicates, at some point there's too much silica in the water and they won't dissolve anymore. And if that's the limitation, then you're absolutely constrained by rainfall. You just have to look at how much rainfall there is in terms of how much goes down rivers. But the silica might be removed by something else. It might go into plants or it might go into a secondary mineral. So if the silica is not limiting, the next thing that becomes limiting is carbonate. As the water goes down the river, are you going to get carbonate precipitating and removing calcium carbonate from the system? It's something that, I've said all that, I think. It's something that Kirsty's been thinking about. To remind you of the basic equation here, she's been thinking about the weathering equation that you show here that consumes CO2 from the atmosphere. She's also thinking in particular about what happens if some of the products reprecipitate. And if they reprecipitate, that partially reverses the equation. So you see that only one carbon is removed instead of two here. If you, one carbon into calcium carbonate rather than two, you do that secondary carbonate precipitation. Kind of running out of time, so I'll just use this as a pretty picture. This just shows the catchments that she's done her modeling in to show you what happens based on the discharge in each catchment and the amount of arable land that you might spread your waste material on, and working out the impact on the rivers that flow through those. So pick your favourite river. I guess you'd be in the Thames catchment here, wouldn't you? So you'd be looking at this catchment here. One of the things that we see really starkly from Kirsty's work is the impact on alkalinity and saturation state in the rivers. And this is just some examples on here. And the natural is blue here on the left of each bar. You can see that the alkalinity is quite low. Basically, that's how much stuff is dissolved in the river. And the saturation state, so how likely it is to start precipitating minerals, is also quite low. And if you do enhanced weathering, even at quite low levels of only 10 tons of silicate per hectare per year, you rapidly get very much higher alkalinity and very much higher saturation state. This is a really big perturbation to river chemistry that you're making, with possible implications for the ecosystem and for secondary precipitation of calcium carbonate. There's lots more to talk about on this slide, but I think it might be good to try and get straight on to some questions rather than prattling on longer. But I think this is a whole area of research that needs to be looked at. What are the implications of pursuing multiple greenhouse gas removal technologies? And for this one, it's not just rivers, but it's groundwaters. If stuff goes into the groundwater, what's that doing there? Or if it goes all the way into the sea, does it stay there in a stable form? Lots of areas where more research is needed. So finally, I'll just say that sort of punchline from Kirsty's work, finally on her study anyway, that if you look at the sort of cancer style modeling result of this, all this goes into the river and flows to the sea. For different amounts of addition, you get quite a large amount of predicted CO2 drawdown. So you can see we're getting close to that 50 million tons equivalent to agriculture on here. If carbonate precipitation is taken into account, the numbers are lower. And if silicate production, if silica saturation becomes the issue, the number is very low. And it's down to less than 1 million tons of CO2 a year. So problems in rivers as well as problems in soils before we start to pursue enhanced weathering. Again, I don't want to suggest this is dead and buried. It's just that these are the sorts of questions we need to work through before we really know the scale it might be useful at and the damage that we might get. I said I'm not going to talk about the oceans, and I think I actually took those slides out. So I've talked about a little bit about BECCS, quite a lot about some of our work on terrestrial weathering. You could go all over this figure, and I'm sure some people in this room are working closer to some of these other boxes on here or thinking more about them. And you can find really important research questions that need to be answered in each one of these boxes, and innovation that might lead to new products and new things that we could then sell around the world. And I'm mentioning that sell around the world thing because there is a lot of money in this area. I mean, really a lot of money. And I've already given you some numbers as I've been through the talk about the research money that's in this field. So 75 million in Defra, 30 million in UKRI, 70 million in BEIS, big lumps of research and innovation money that are coming in to try and solve these problems, and which are an incentive for researchers around the country. But then if you also look at the size of the carbon market, where banks and industries and IT companies are all trying to buy carbon credits, the amount of money that's slopping around in that system is pretty astronomical. And this is where I probably could have used my notes. I've got some summaries on the bottom of here, but you can see some numbers on here, that the size of the overall carbon market, how much is traded each year. This is in, I've forgotten what year it is. Oh no, sorry, the years are down here. 2021, I'm getting close to $1 trillion US dollars of basically money for carbon, that's being traded around here. And the carbon and the voluntary carbon offsets here. Forgot what my units are here. Never mind. Numbers are really big. I won't make up a number of you get it wrong. But the numbers of the carbon budgets are astronomical, and that's where that research is facing into, as well as, of course, working out how to save our planet and stopping it from overheating and causing the climate warming that we're all keen to avoid. So thanks very much for listening.
Okay, thank you very much to Gideon. Sorry, that was quite loud. We do now have some time for questions. We have a couple of different audiences because this is a hybrid event. So we have obviously the room here. We also have our Silwood Park campus, which has an in-person viewing session. And we have all of our online viewers as well. So I think the easiest way to do that is we'll start with questions in this room. If you are online and you have a question, the best way to get it to us is to put it in the chat, and we'll pass it on to Gideon here. And if anyone at Silwood Park has a question, then Patrick, if you could just raise the hand of the Silwood Park camera, and we will go to you to take those questions. So let's start with this room. Does anyone have any questions for Gideon? Yes, just wait, if I can bring the microphone over to you so everyone can hear.
Hello, thank you. That was really interesting. I was just going to ask about, I know you purposely didn't have time to mention it, but with the ocean stuff, I was going to ask about, obviously the aim is to store it for long timescales in the deep ocean, and I wondered how much of it, if there was an idea of how much of this carbonate from the weathering gets actually into the deep ocean, or instead is recycled to the atmosphere again.
Yeah, it's a good question. I think it's one of the really most fundamental questions here. And our research on that is a little less advanced, which is why I didn't show so much of it. The bicarbonate that goes down the rivers when it makes it to the ocean is very stable. There's already 40 times more carbon as bicarbonate in the ocean than there is in the atmosphere. So you can add a bit more to that without any problem. It's not going to become CO2 and go out that way. But what it might do is because that process increases the saturation state of the ocean, biology might respond to that, biology that makes shells, so corals and mollusks and things. And that if those shells grow more quickly, they will take some of the carrying capacity of the ocean away again. So they'll kind of reverse the process you're trying to achieve. I showed the reaction, I went through it very quickly, but the reaction I talked about in rivers of calcium carbonate precipitation actually releases some CO2 to the atmosphere. So if the ocean accelerates its carbonate precipitation, the same thing will happen. So it will effectively make it less efficient as a scheme. But I think it's probably safe to say it's not dangerous to the ocean. It might just be that we've wasted our time. We put it in the ocean and it hasn't done as much as we hoped it would do.
Thank you.
So normally the first question is the difficult one, and there's some more. And this audience was confounding me.
Thank you so much for your talk, Gideon. I mean, so many questions raised by everything, but I'll ask some policy questions instead. I was going to ask, you mentioned obviously Defra focuses on agricultural emissions, and then you focused on two methods that sort of use agricultural land as forms of carbon capture. But I was wondering, from an accounting point of view, do emissions that are sort of or carbon that's sequestered through techniques that are on agricultural land, does that go to offset agriculture's emissions, or does it depend who's paying for it, and how do you account it up and things like that? Because it strikes me that there might not be the money in agriculture necessarily to pay for agricultural land techniques that are offsetting carbon in that way.
Yeah, there's a lot. I mean, there's a lot in this field, isn't there? So I'll give you a long answer. I'll try not to. But the atmosphere doesn't care where the carbon or methane or nitrous oxide came from. So there isn't an attempt to sort of say, well, you should be balancing off one thing at a time. And the effort share that's apportioned to the different departments is not just done on a, okay, we've got to get 78% reductions, let's do that in every sector. It is done based on some analysis, Committee for Climate Change and other analysis saying which sectors are easier to decarbonise than others and can afford it more than others. So the 31 million tonnes that we've got to achieve is not as stringent, not as low a bar as some other departments, because agriculture really is quite a tricky one to decarbonise. But it is, I mean, the money that's going around in like I showed you on the last slide is generally fairly agnostic about where it goes. If they think there's actually a verifiable store of carbon or a way of reducing emissions, that money will flow into it, regardless of whether it's cars or agriculture or whatever. So the financial aspects are not really the blocker. I think the challenge with the biggest difference between sucking out oil from the subsurface and doing something with agriculture is the permanence. With agriculture, if you grow more trees, you're not completely convinced that those trees are going to be there forever. If you suck the oil out of the ground and burn it, you damn well know the carbon dioxide is going to be there forever. So it's the permanence issue is probably the biggest differentiator, I think.
Thank you so much. And just a quick follow-up question, if I'm allowed. Obviously, the government's decided not to appeal the ruling earlier this year that the carbon, the net zero strategy that you outlined in the document was unlawful, or parts of it were unlawful. I was wondering if there is any recalibration within the targets that are within Defra's scope to produce the sort of revised net zero strategy for March next year, or whether that's all falls outside of Defra's.
I think I am gonna take the night for that one and say that's Base's problem, not ours. The judicial, we've got enough judicial reviews to worry about without having to worry about that one as well. Get into air quality and water quality and things. But that is Base's problem. I'm not quite sure how they're planning to respond to it. In some ways, I find it quite unfortunate, actually, the fact that this is the UK has, as I said a few times, really been leading the charge on this, trying to take the rest of the world with us, and then to sort of lay into something which isn't perfectly lining out how you get to 78% reduction seems a bit cruel, but we are where we are.
We do have a couple of online questions at the moment. So.
Yeah, it's been great to see that the chat is actually pretty lively. So first up is Ruben Nixon Hill, who's asking, how do or might the impacts of enhanced weathering compare to typical effects of current agriculture on the ecosystem?
That's an excellent question. I don't think I've ever stopped to think about that. Because, I mean, we know that agriculture is doing a great deal of damage, or has globally done a great deal of damage. I'm looking at you like you asked the question, but that's just natural. We know that agriculture has done a great deal of damage to biodiversity and is responsible for a lot of our carbon emissions. So the agricultural system itself is damaging. But we have to do it, right? We've got to eat something. So we've got to keep doing agriculture. It's kind of a given that that continues. But setting greenhouse gas removal approaches like enhanced weathering into that context, I think is a good one to do. I don't have an answer, but it's a good question. It's a good challenge. But I guess we're not quite ready to know just how damaging it is because we're early in the research process, but that would be a good way of playing some research.
Can I go for another one from online?
Yeah, I'm fine. Yeah,
there's quite a few. I guess we'll take one. Yeah. So, are there any major differences in how general public or scientific community respond to this type of messaging compared to how policymakers respond to this information? Like,
was the question to say what information?
No, I assume in general. It came when you were answering Henry's question.
I think the problem it's inherent in the question is what are the public? What are the public? Because the public have a very wide range of views, from people who say that we should just damn well get on and build houses and stop worrying about the environment, to people who throw tins of tomato soup at Van Gogh. And somewhere in that wide range, it's hard to average what the public think about this space. But certainly, if you look at the how climate change features on people's sort of voting intentions and their importance radar, it's much higher than it used to be, and normally in the top 3 for most people. And actually, that's true in many nations around the world as well. So the public are very concerned about these sorts of issues. And I do think that has been one of the drivers that's made policymakers concerned as well. It's partly the fact that they know their voters care, that they are kind of forced into action. So I'll answer it as a chicken and egg question. It's the public concern in democratic countries that's leading to the policy concern.
More questions in the room?
Yes, did we have one up there? No? Any other questions in the room?
Hi. Has there been any change in the public perception of what we used to refer to as geoengineering? I know we are rebranding it, so it's not as bad sounding, but as you described how we've changed globally and nationally, has that changed?
Yeah, rebranding is an interesting choice of words, and I've used it myself in other debates, like Windscale, the nuclear power plant being rebranded as Sellafield, and that wasn't explicit rebranding because they thought it was damaged goods. They changed the name. I don't think that works. I think more people see through it normally. So I guess I take a bit of umbrage with your accusation that geoengineering is being rebranded as greenhouse gas removal. The time that geoengineering really hit the headlines, I think, was in 2009. I think that's the right year when the Royal Society wrote a report about geoengineering. And at that point, they very explicitly divided it into two different approaches that are quite distinct. One is greenhouse gas removal, which I've spoken about and has become completely mainstream. And people really believe we have to do it if we're going to solve the climate problem. And the other one is solar radiation management, where you actually block out some of the, where you actually block out some of the sunlight. It doesn't want to stay anymore. You block out some of the sunlight before it reaches the planet. And that has an imbalance between infrared and ultraviolet radiation. It causes a spatial pattern of change that's not recommended. And it increases the sulfate concentration of the atmosphere. Depends what you use, but probably leads to acid rain. So lots of big negatives about that form of geoengineering and lots of big positives about the one I've spoken about. They're very different from each other. And I think my impression is that the public is as hostile as ever to the solar radiation management, but is quite accepting of greenhouse gas removal, depending on the technology. If you're going to dump a bunch of iron in the ocean, people get quite protective about that. If you're going to grow a bunch of trees, people are normally quite happy. So that answers your question.
I think we're probably out of time for questions now. A lot have come through online, and we're really grateful to everyone for engaging so much with this talk. But we can't take any more of Gideon's precious time. Thank you so much to everyone for coming. I just want to let you know that we will have a drinks reception now, just outside upstairs, I think. Yes, so just outside there will be a drinks reception. Hopefully you can hang around for a bit longer so people can talk to Gideon a bit more outside. But I would just like to end by thanking Gideon again, and one final round of applause for your Okay, before you all go, we have some other seminars to advertise. And the first one that's coming up is the Grantham Institute's annual lecture, which is on the 23rd of November. And we also have 4 more Changing Planet seminars coming up. December, January, February, and March are all in the calendar. So take a photo of this, or all of the information will be online on the Grantham Institute's website. But yeah, we've got some really exciting talks coming up on a really wide range of topics. So please do come along. And thank you very much.
Take this off for me.
Fantastic.
Well, there's a lot of material, but I rattled through it and seem to do it in the time reference.
It's a lot to